Cosmic rays are immensely high-energy radiation, mainly originating outside the solar system. They may produce showers of secondary particles that penetrate and impact the Earth's atmosphere and sometimes even reach the surface. Composed primarily of high-energy protons and atomic nuclei, they are of mysterious origin. Data from the Fermi Space Telescope has been interpreted as evidence that a significant fraction of primary cosmic rays originate from the supernovae of massive stars. However, this is not thought to be their only source. Active galactic nuclei probably also produce cosmic rays. The term ray is an historical accident, as cosmic rays were, at first, and wrongly, thought to be mostly electromagnetic radiation. In common scientific usage, high-energy particles with intrinsic mass are known as cosmic rays, and photons, which are quanta of electromagnetic radiation, are known by their common names, such as gamma rays or X-rays, depending on their origin. Cosmic rays attract great interest practically, due to the damage they inflict on microelectronics and life outside the protection of an atmosphere and magnetic field, and scientifically, because the energies of the most energetic ultra-high-energy cosmic rays have been observed to approach 3 times 1020 electron volts, about 40 million times the energy of particles accelerated by the Large Hadron Collider. One can show that such enormous energies might be achieved by means of the centrifugal mechanism of acceleration in active galactic nuclei. At 50 J, the highest energy ultra-high-energy cosmic rays have energies comparable to the kinetic energy of a 90 km/h baseball. As a result of these discoveries, there has been interest in investigating cosmic rays of even greater energies. Most cosmic rays, however, do not have such extreme energies. The energy distribution of cosmic rays peaks at 0.3 GeV. Of primary cosmic rays, which originate outside of Earth's atmosphere, about 99% to the nuclei of well-known atoms, and about 1% to solitary electrons. Of the nuclei, about 90% are simple protons, hydrogen nuclei, 9% are alpha particles, and 1% to the nuclei of heavier elements, called Hz ions. A very small fraction are stable particles of antimatter, such as positrons or antiprotons. The precise nature of this remaining fraction is an area of active research. An active search from Earth orbit for anti-alpha particles has failed to detect them. History. After the discovery of radioactivity by Henri Becquerel and Marie Curie in 1896, it was generally believed that atmospheric electricity, ionization of the air, was caused only by radiation from radioactive elements in the ground or the radioactive gases or isotopes of radon they produce. Measurements of ionization rates at increasing heights above the ground during the decade from 1900 to 1910 showed a decrease that could be explained as due to absorption of the ionizing radiation by the intervening air. Discovery in 1909, Theodore Wolff developed an electrometer, a device to measure the rate of ion production inside a hermetically sealed container, and he used it to show higher levels of radiation at the top of the Eiffel Tower than at its base. However, his paper published in Physikalische Zeitschrift was not widely accepted. In 1911, Domenico Pacini observed simultaneous variations of the rate of ionization over a lake, over the sea, and at a depth of 3 meters from the surface. Pacini concluded from the decrease of radioactivity underwater that a certain part of the ionization must be due to sources other than the radioactivity of the Earth. In 1912, Victor Hess carried 3 enhanced accuracy Wolf electrometers to an altitude of 5,300 meters in a free balloon flight. He found the ionization rate increased approximately 4-fold over the rate at ground level. Hess ruled out the Sun as the radiation source by making a balloon ascent during a near-total eclipse. With the Moon blocking much of the Sun's visible radiation, Hess still measured rising radiation at rising altitudes. He concluded, "The results of my observation are best explained by the assumption that a radiation of very great penetrating power enters our atmosphere from above, in 1913–1914. Werner Kohlhorster confirmed Victor Hess' earlier results by measuring the increased ionization rate at an altitude of 9 kilometers. Hess received the Nobel Prize in Physics in 1936 for his discovery. The Hess balloon flight took place on 7 August 1912. By sheer coincidence, exactly 100 years later on 7 August 2012, the Mars Science Laboratory rover used its radiation assessment detector instrument to begin measuring the radiation levels on another planet for the first time. On 31 May 2013, NASA scientists reported that a possible manned mission to Mars may involve a greater radiation risk than previously believed, based on the amount of energetic particle radiation detected by the RAD on the Mars Science Laboratory while traveling from the Earth to Mars in 2011–2012. Identification. In the 1920s, the term cosmic rays was coined by Robert Millikan, who made measurements of ionization due to cosmic rays from deep underwater to high altitudes and around the globe. Millikan believed that his measurements proved that the primary cosmic rays were gamma rays, i.e., energetic photons, and he proposed a theory that they were produced in interstellar space as byproducts of the fusion of hydrogen atoms into the heavier elements, and that secondary electrons were produced in the atmosphere by Compton's scattering of gamma rays. But then, in 1927, Clay found evidence, later confirmed in many experiments, of a variation of cosmic ray intensity with latitude, which indicated that the primary cosmic rays are deflected by the geomagnetic field and must therefore be charged particles, not photons. In 1929, Bothe and Kohlhorster discovered charged cosmic ray particles that could penetrate 4.1 centimeters of gold. Charged particles of such high energy could not possibly be produced by photons from Millikan's proposed interstellar fusion process. In 1930, Bruno Rossi predicted a difference between the intensities of cosmic rays arriving from the east and the west that depends upon the charge of the primary particles, the so-called east-west effect. 3 independent experiments found that the intensity is, in fact, greater from the west, proving that most primaries are positive. During the years from 1930 to 1945, a wide variety of investigations confirmed that the primary cosmic rays are mostly protons, and the secondary radiation produced in the atmosphere is primarily electrons, photons and muons. In 1948, observations with nuclear emulsions carried by balloons to near the top of the atmosphere showed that approximately 10% of the primaries are helium nuclei and 1% are heavier nuclei of the elements such as carbon, iron, and lead. During a test of his equipment for measuring the east-west effect, Rossi observed that the rate of near-simultaneous discharges of 2 widely separated Geiger counters was larger than the expected accidental rate. In his report on the experiment, Rossi wrote, "It seems that once in a while the recording equipment is struck by very extensive showers of particles, which causes coincidences between the counters, even placed at large distances from one another." In 1937, Pierre Auger, unaware of Rossi's earlier report, detected the same phenomenon and investigated it in some detail. He concluded that high-energy primary cosmic ray particles interact with their nuclei high in the atmosphere, initiating a cascade of secondary interactions that ultimately yield a shower of electrons and photons that reach ground level. Soviet physicist Sergei Vernov was the first to use radiosondes to perform cosmic ray readings with an instrument carried to high altitude by a balloon. On 1 April 1935, he took measurements at heights up to 13.6 kilometers using a pair of Geiger counters in an anti-coincidence circuit to avoid counting secondary ray showers. Homi J. Barber derived an expression for the probability of scattering positrons by electrons, a process now known as Barber scattering. His classic paper, jointly with Walter Heitler, published in 1937, described how primary cosmic rays from space interact with the upper atmosphere to produce particles observed at the ground level. Barber and Heitler explained the cosmic ray shower formation by the cascade production of gamma rays and positive and negative electron pairs. Energy distribution measurements of the energy and arrival directions of the ultra-high energy primary cosmic rays by the techniques of density, sampling, and fast timing of extensive air showers were first carried out in 1954 by members of the Rossi Cosmic Ray Group at the Massachusetts Institute of Technology. The experiment employed 11 scintillation detectors arranged within a circle 460 meters in diameter on the grounds of the Agassiz station of the Harvard College Observatory. From that work, and from many other experiments carried out all over the world, the energy spectrum of the primary cosmic rays is now known to extend beyond 1020 electron volts. A huge air shower experiment called the Auger Project is currently operated at a site on the pampas of Argentina by an international consortium of physicists, led by James Cronin, winner of the 1980 Nobel Prize in Physics from the University of Chicago, and Alan Watson of the University of Leeds. Their aim is to explore the properties and arrival directions of the very highest energy primary cosmic rays. The results are expected to have important implications for particle physics and cosmology. Due to a theoretical Gree-Sensat-Sepin-Kuzmin limit to the energies of cosmic rays from long distances which occurs above 1020 electron volts because of interactions with the remnant photons from the Big Bang origin of the universe. High-energy gamma rays were finally discovered in the primary cosmic radiation by a MIT experiment carried on the OS-03 satellite in 1967. Components of both galactic and extragalactic origins were separately identified at intensities much less than 1% of the primary charged particles. Since then, numerous satellite gamma-ray observatories have mapped the gamma-ray sky. The most recent is the Fermi Observatory, which has produced a map showing a narrow band of gamma-ray intensity produced in discrete and diffuse sources in our galaxy, and numerous point-like extragalactic sources distributed over the celestial sphere. Types. Cosmic rays can be divided into two types: galactic cosmic rays, high-energy particles originating outside the solar system, and solar energetic particles, high-energy particles emitted by the Sun, primarily in solar particle events. However, the term cosmic ray is often used to refer to only the GCR flux. Despite the nomenclature, galactic GCRs may originate within or outside the galaxy. Cosmic rays originate as primary cosmic rays, which are those originally produced in various astrophysical processes. Primary cosmic rays are composed primarily of protons and alpha particles, with a small amount of heavier nuclei and an extremely minute proportion of positrons and antiprotons. Secondary cosmic rays, caused by a decay of primary cosmic rays as they impact an atmosphere, include neutrons, pions, positrons, and muons. Of these four, the latter three were first detected in cosmic rays. Primary cosmic rays primarily originate from outside the solar system and sometimes even the Milky Way. When they interact with Earth's atmosphere, they are converted to secondary particles. The mass ratio of helium to hydrogen nuclei, 28%, is similar to the primordial elemental abundance ratio of these elements, 24%. These nuclei appear in cosmic rays in much greater abundance than in the solar atmosphere, where they are only about n-11 as abundant as helium. Cosmic rays made up of charged nuclei heavier than helium are called HZ ions. Due to the high charge and heavy nature of HZ ions, the contribution to an astronaut's radiation dose in space is significant even though they are relatively scarce. This abundance difference is a result of the way secondary cosmic rays are formed. Carbon and oxygen nuclei collide with interstellar matter to form lithium, beryllium and boron in a process termed cosmic ray spallation. Spallation is also responsible for the abundances of scandium, titanium, vanadium, and manganese ions in cosmic rays produced by collisions of iron and nickel nuclei with interstellar matter. Primary cosmic ray antimatter satellite experiments have found evidence of positrons and a few antiprotons in primary cosmic rays, amounting to less than 1% of the particles in primary cosmic rays. These do not appear to be the products of large amounts of antimatter from the Big Bang, or indeed complex antimatter in the universe. Rather, they appear to consist of only these two elementary particles, newly made in energetic processes. Preliminary results from the presently operating alpha magnetic spectrometer on board the International Space Station show that positrons in the cosmic rays arrive with no directionality, and with energies that range from 10 GeV to 250 GeV. In September 2014, new results with almost twice as much data were presented in a talk at CERN and published in Physical Review Letters. A new measurement of positron fraction up to 500 GeV was reported, showing that positron fraction peaks at a maximum of about 16% of total electron plus positron events, around an energy of 275 plus or minus 32 GeV. At higher energies, up to 500 GeV, the ratio of positrons to electrons begins to fall again. The absolute flux of positrons also begins to fall before 500 GeV, but peaks at energies far higher than electron energies, which peak about 10 GeV. These results on interpretation have been suggested to be due to positron production in annihilation events of massive dark matter particles. Cosmic ray antiprotons also have a much higher energy than their normal matter counterparts. They arrive at Earth with a characteristic energy maximum of 2 GeV, indicating their production in a fundamentally different process from cosmic ray protons, which on average have only 1/6 of the energy. There is no evidence of complex antimatter atomic nuclei, such as antihelium nuclei, in cosmic rays. These are actively being searched for. A prototype of the AMS-02, designated AMS-01, was flown into space aboard the Space Shuttle Discovery on STS-91 in June 1998. By not detecting any antihelium at all, the AMS-01 established an upper limit of 1.1 times 10⁻⁶ for the antihelium to helium flux ratio. Secondary cosmic rays. When cosmic rays enter the Earth's atmosphere, they collide with atoms and molecules, mainly oxygen and nitrogen. The interaction produces a cascade of lighter particles, a so-called air shower secondary radiation that rains down, including X-rays, muons, protons, alpha particles, pions, electrons, and neutrons. All of the produced particles stay within about 1 degree of the primary particle's path. Typical particles produced in such collisions are neutrons and charged mesons such as positive or negative pions and kaons. Some of these subsequently decay into muons, which are able to reach the surface of the Earth, and even penetrate for some distance into shallow mines. The muons can be easily detected by many types of particle detectors, such as cloud chambers, bubble chambers or scintillation detectors. The observation of a secondary shower of particles in multiple detectors at the same time is an indication that all of the particles came from that event. Cosmic rays impacting other planetary bodies in the solar system are detected indirectly by observing high-energy gamma-ray emissions by gamma-ray telescope. These are distinguished from radioactive decay processes by their higher energies above about 10 MeV. Cosmic ray flux. The flux of incoming cosmic rays at the upper atmosphere is dependent on the solar wind, the Earth's magnetic field, and the energy of the cosmic rays. At distances of 94 astronomical units from the Sun, the solar wind undergoes a transition, called the termination shock, from supersonic to subsonic speeds. The region between the termination shock and the heliopause acts as a barrier to cosmic rays, decreasing the flux at lower energies by about 90%. However, the strength of the solar wind is not constant, and hence it has been observed that cosmic ray flux is correlated with solar activity. In addition, the Earth's magnetic field acts to deflect cosmic rays from its surface, giving rise to the observation that the flux is apparently dependent on latitude, longitude, and azimuth angle. The magnetic field lines deflect the cosmic rays towards the poles, giving rise to the aurora. The combined effects of all of the factors mentioned contribute to the flux of cosmic rays at Earth's surface. The following table of participial frequencies reach the planet and are inferred from lower energy radiation reaching the ground in the past. It was believed that the cosmic ray flux remained fairly constant over time. However, recent research suggests 1.5 to 2-fold millennium timescale changes in the cosmic ray flux in the past 40,000 years. The magnitude of the energy of cosmic ray flux in interstellar space is very comparable to that of other deep space energies. Cosmic ray energy density averages about 1 electron-volt per cubic centimeter of interstellar space, or 1 electron-volt per cc, which is comparable to the energy density of visible starlight at 0.3 electron-volts per cc, the galactic magnetic field energy density which is 0.25 electron-volts per cc, or the cosmic microwave background radiation energy density at 0.25 electron-volts per cc.